All right, in this problem, we have a sample of oxalic acid of unknown concentration, and that would be our analyte. We're analyzing this acid solution. We don't know its molarity. To figure out its molarity, we are going to titrate it with potassium permanganate that we do know the concentration of. And we do have to know the balance equation in order to do these calculations. So the student does the titration until a faint pink color is observed. That's how he knows that the reaction is done. We have completely reacted all of the acid with the potassium permanganate, and we're going to stop the titration there and record the volume of potassium permanganate needed to complete this reaction. And we'd already determined that 19.15 milliliters of that potassium permanganate were needed to complete this reaction and react with all of the acid. The key here in a titration is we add just enough of the titrant to completely react with the analyte. We try not to add excess titrant because we're using that volume of titrant in our calculation of moles of titrant, and we want to be as in line with the stoichiometric ratios as possible. But before we dive into the calculations, I just want to give you a brief overview, a reminder of what's going on here. In step 1 of a titration, you have your burette filled with your titrant. In our case, our titrant is this potassium permanganate. Okay, it's this purplish solution, so that's why it's colored purple here in the burette. Notice here that this stopcock is closed. It's this little turnable valve, and when it's horizontal, flat, it is in the off position. No solution is going to run out of that burette. In the flask is what we're analyzing. That's going to be our oxalic acid, and we know we're going to put 25 milliliters of the acid into our flask. We just don't know the molarity of what is inside of our flask. Step 2 of our titration, once we're all set up, we open the stopcock. Now that is in the vertical position. Now you'll see that the solution from the burette is dripping out. You'll notice that the volume has gone down a little bit. And so we are now going to react that potassium permanganate with the acid. We continue adding the titrant until we know that the reaction is complete. And for this particular reaction, we know it's complete when we reach the pale pink color in the flask. And so we immediately close the stopcock and we measure the volume of potassium permanganate in the burette, and we calculate how much potassium permanganate was needed to reach this equivalence point. So notice from start to finish that the potassium permanganate volume inside of the burette goes down throughout the titration, and that's because we are dispensing it here in the bottom. And so this is the key part. We have figured out in our problem the necessary volume potassium permanganate to reach the equivalence point. So our first step in a calculation would be to take the volume of the titrant, potassium permanganate, that purple stuff, and convert it into liters, and then convert it into moles. So that's what I've done right here. I've taken our 19.15 milliliters, converted over to liters, and then using the molarity of the potassium permanganate, 0.031 moles per liter, we're going to calculate the moles of potassium permanganate. Now, we know the potassium permanganate is one of our reactants, so we can use this and stoichiometry to figure out how many moles of the acid reacted with our potassium permanganate. Now, looking at your balance equation, you might be wondering, well, there is no potassium permanganate in our balance equation. There's no KMnO4, but we do have this MnO4, the permanganate ion. And that's the one that we're going to use because what we're really looking at here is the balance net ionic equation. So potassium here is a spectator ion, so that's why it doesn't appear in our balance net ionic equation. So what we're going to want to do is first convert from moles of potassium permanganate into moles of permanganate ions, but we know that it is a 1-to-1 ratio because there's one permanganate ion inside of one potassium permanganate because its subscript is 1. This allows me to calculate moles of permanganate ion. And then comes the stoichiometry part. Now we're ready for that mole ratio, and using those coefficients from the balance equation, we're going to set up our ratio of 5 moles of oxalic acid for every 2 moles of permanganate ion. I have my mole ratio now in my dimensional analysis, and now I'm just going to calculate the moles of oxalic acid that were in the flask. Okay, so we can see here that in our flask at the beginning, there were 1.48 times 10 to the negative third moles of oxalic acid. So we have just used the volume of our titrant, the molarity of our titrant, to get the moles of the titrant. Then we use the balance equation and stoichiometry to get moles of the acid, what we're analyzing. And then for one final step, they would like us to calculate the molar concentration of the original acid solution that we put in the flask. So we're going to need to set up our molarity equation. Okay, I have my equation for molarity of the oxalic acid. And remember, they want the initial concentration of that acid that we put into the flask. So I'm being very intentional here. I am writing initial concentration, moles, initial acid, and then liters of the initial acid solution. So we're going to plug and chug here. Plugging in the moles that I got from my dimensional analysis and stoichiometry and the volume of 0.025 liters. That was how much acid we started with in the beginning. You'll see here that our acid had a molar concentration of 0.059 moles per liter. So essentially what we did here is we did a titration reaction, which allows us to figure out how many moles of analyte we put in the flask, and then we take those moles and we divide by the volume of the analyte that we put in the flask, and there you have it. We have the molar concentration of the analyte, the solution that we are trying to analyze because we did not originally know its concentration.